Algebra 2, Chapter 16.1, Exercises 13 through 20. In this exercise set, we're going to work over some real-world problems in using logarithms. And we're going to be using these properties of logarithms, definition-based properties, especially this one here and this one, product property, quotient property, power property, and change of base property, all of those properties. Finance, a stock priced at $40 increases at a rate of 8% per year. Write and evaluate a logarithmic expression for the number of years that will take for the value of the stock to reach $50. Now you might remember back from chapter 13, we looked at something called exponential functions where we had an amount, a of t equals a sub 0 times 1 plus r to the power of t. And what these different things are, this whole 1 plus t is called the base of an exponential function. This a sub 0 is the starting amount. This a sub t is the final amount. So let's go ahead and work and put the elements for this situation in place. Well, a stock priced at $40, that's going to be our initial amount. Okay, that's where that comes from. Times our base. Well, what happens is, that's 8%. This is called our value of r. It's 8%. But in decimal form is what we really need, which is 0.08. So what we have here is 40 times 1 plus 0.08 to the power of t, and then that is equal to our final amount, $50. So here in place are all the elements we need to solve this equation. Now, in chapter 13, we actually would solve an equation like this by graphing an exponential function and seeing where they intersect. Here we're going to solve this without a graphing calculator. And to do that, we're going to first divide by 40 on both sides of the equation. So we get 1.25 is equal to 1.08 to the power of t. Now what we're going to do is, in the process of isolating the t, we're going to take the logarithm of both sides of the equation. So we have log of 1.25. When we say log, we're talking about log base 10. So log of 1.25 equals the log of 1.08 to the power of t. And using the power property of logarithms, which is right here, if we have log base b of m to the n power, that's equal to taking this n out front. And that's what we're going to do exactly here with this t. So we have log of 1.25 equals t log of 1.08. Now we're going to divide both sides of this equation by log 1.08. So we have t is equal to the quotient of log 1.25 and log 1.08. And we go to our calculator. And what I did is previously I worked this up above at the top, log 1.25, and here's the log key right here. So that's how you put that log key in place. Anyway, you get 2.899, which rounds to 2.90. So 2.90. And so this will be t equals, we'll say approximately equal, 2.9 years. And that will be our answer, without using the graphing element of our calculator, just the log key. Because of change of base formula, we could have put the natural log of either, because essentially the change of base formula is what allows us to solve this way. Okay. 14. I'm not going to work out 14 here in the tradition of not working out the even number problems, but here we have our base. Our base is equal to 1 plus r. Well, in this case, r is equal to, we have a decreasing rate, is equal to negative 4%, which equals negative 0.04. And so we'll have to take that into account in working this out. Next, 15. The population P of bacteria in a culture after T minutes is given by the equation P equals P sub 0. Now, in the other problem 13, I used A sub T and A sub 0, but it's the same type of situation here. So we have the initial bacteria count, which is 200. That's going to be our P sub 0. So we have 200 times 1.12 to the power of T. And our final amount is, the bacteria is 1,000. So this problem is actually, I believe, easier than problem 13 in that our equation is already given to us. So on the left side, we have 5 equals 1.12 to the power of T. We take the logarithm of both sides of the equation. So we have log of 5 is equal to log of 1.12 to the power of T. And using the power property of logarithms, we can rewrite this equation as log base 5, log base 10 of 5, which is log 5, equals T log of 1.12, and dividing both sides by log 1.12, we have, I'll work to the right here, T is equal to log of 5 over log of 1.12. And that's going to be equal to, and again, we're going to use a calculator. And previously I put that in place. We got 14.201. So I'll say 14.2. And so using that 14.2, how long will it take for the population to decrease or to increase to 1,000? We'll say about 14.2. And what are the units here? Minutes. So that will be our answer to problem number 15. Next problem, let me talk about 16 a little bit. We have most swimming pool experts recommend a pH between 7.0 and 7.6. So what you do for this one is you want to find two numbers, one found from the 7.0 and one found from the 7.6. What you do is you take 7.0 is equal to negative log, that's log base 10 of a hydrogen ion concentration. And what you're going to do is work about solving for this hydrogen ion concentration. And I'll leave it to the viewer to do that. 17, match the logarithmic expressions to equivalent expressions. So we have 5 A, B, C, D, E to do here. And what I'm going to do for this is just work these through one at a time. And so I'm going to have to kind of erase as I go. But just working out A, we're going to rewrite this. You have a product of two factors here. So using the product property, this is going to be equal to log base 2 of 4 plus log base 2 of x. Okay, now we're going to rewrite this log base 2 of 4 as log base 2 of 2 squared. So 4 is replaced by 2 squared. I'm just going to carry over the log base 2 of x. And using the power property, this is going to be equal to 2 log base 2 of 2 plus log base 2 of x. And going back to our original identity, log base 2 of 2, what power do we have to raise 2 to equal 1? Well, that's going to be 1. So this log base 2 of 2 is 1. So our answer here is 2 plus log base 2 of x. And so that's going to be this one right here. So that'll be A. I'll just put A right here. Okay, now I'm going to work this second one. I normally like to leave it up for the whole problem, but I'm going to erase this. Okay, next, B. We have a quotient, so we're going to rewrite this logarithm as a difference. So that's going to be equal to log base 2 of x minus log base 2 of 4. And so this is going to be equal to log base 2 of x minus log base 2 of 2 squared. And what we're going to do is we're going to use the power property. So this is going to be 2 log base 2 of 2, and log base 2 of 2 is 1. So this is going to be equal to log base 2 of x minus 2. And that's going to be right down here. B is right down there, this last one. Okay, next. Log base 2 of 4 to the x power. Well, what that's going to be is log base 2, and I'm going to rewrite 4 as 2 squared. Okay, so what this is going to be is log base 2 of 2 to the power of 2x. And using the power property, this is is going to be equal to, we take this 2x out front, we're going to have 2x log base 2 of 2. And what is log base 2 of 2? It's 1. So our answer here is going to be 2x. So that's going to be C right here. Okay. Next, D. We have log base 2 of x to the 4th power. Well, that's going to be our power property. So it's going to be 4 log base 2 of x. And so that's, we really don't have anything more to do here. That's going to be D right here. And then by process of elimination, we already know what E is going to have to be. We're going to use, in this case, a change of base formula. Log base 2 of x is going to be log of x divided by log of 2. And the change of base formula was more important originally than it is now, because like the calculator keys, for instance, have just a log and an ln key. Now there's additional function involved here. If you go to math and go down here to log base, you can here put a base other than 10 or E, but we're not going to do that here in this exercise. So that's number 17. Prove the quotient property of logarithms. I'm going to let that go, and we're going to go to prove the change of base property of logarithms. Justify each step of your proof. And these ones here, 18 on, are kind of advanced, and you'll see these sometimes in college textbooks. I'm going to go ahead and do this one. 19, prove the change of base property of logarithms. Justify each step of your proof. And what I did is I previously wrote down what the change of base formula is. And what we're going to do, our first step, we're going to say let x equals log base c of a. So let x equal log base c of a. Then what we're going to do is we're going to change this c to what power equals a. So that's going to be rewritten as an exponential equation as c to the x power is equal to a. So that's the definition of logarithm. So what we have is log, we're going to write this log base b of a equals log base b of c to the power of x. Okay, so we're introducing the b to show a common base for a different logarithm than either a or c. So anyway, we're going to use the power property on the right side. So log base b of a is equal to x log base b of c. Okay, and then we can solve for x, and what we're going to do is divide both sides by log base b of c log base b of c, and they cancel out. So x is equal to log base b of a over log base b of c. And we already said at the beginning that let x equal log base a of c. So replacing x, log base c of a is equal to log base b of a over log base b of c. So that is the proof of the change of base property of logarithms. And then problem 20 is a multi-step problem, which is really not that hard. It's really similar to like problem 14, where you have, this is going to be our value of r, and then you can take this a of t equals a sub 0, base is 1 plus r to the power of t, and then you can solve for you can put in 100 for a of t, 250 for a sub 0, and then find your base. Using this is going to be r is equal to 0.0121%, which is equal to 0.000121. So anyway, then there's part B, the half-life. So anyway, that's it. I hope this has been helpful to you. Thanks for viewing.